So I want to go ahead and give a brief overview of the second lecture. And the third lecture I'll make sure I've got up as well. So the first one, where we really started to begin to consider the information, was considering digital systems and binary numbers. So the digital systems are the world that we're going to be in. We're going to use digital electronics to create our systems. And the fundamental building block of a digital system is the transistor. And the transistor is able to represent a value either high or low. You might think of the light switch in your house as either being on or off. Or for us, we'll call it a 1 or a 0. So our world is going to be built around a collection of transistors that will be able to produce one or more binary values. Some of the terminology we want to get out of the way is that a bit is what we refer to as a single binary digit. Sometimes we could refer to it as a 0 or a 1. When we talk about 1 bit, we call that a scalar. If we have a collection of bits, let's say more than 1, 2, 5, 8, 12, we would call that a vector. And there's a special designation given to a vector of 8 bits, and that's called a byte. In the past, they referred to a collection of 4 bits as a nibble, but this is really not used too much anymore. So when we come to the values represented within a computer, you have to keep in mind that it's the context that determines what you interpret that value as. As we're learning here, and we'll see a little bit more, is that one way is to represent values. So if you're creating a spreadsheet where you want to create the salary of all your employees, you want to be dealing with numerical values. On the other hand, the numbers inside the computer sometimes represent codes. Sometimes it's the opcode if you have the executable code running in your machine. More commonly, it may be a code to display the characters on a screen. And we'll see, we call that an ASCII code. We'll see that in a moment. We're going to primarily focus on the numeric values. And to get going, we'll look at the first 16 decimal digits, and we'll see that we're primarily contrasting the decimal world to the binary world. But there's two other bases, base 8 and base 16, which just give us a way to encapsulate representations of binary values. And by that I mean that a hexadecimal is a collection of 4 binary digits. An octal digit is a collection of 3 binary digits. And we look to the right, we can see the first 16 decimal values, 0 to 15. You can see their binary representation. They represent the hexadecimal values from 0 to F. So the first thing to remember always is that each hexadecimal digit represents 4 binary digits. And then each octal digit is represented by 3 binary digits. And when we count in octal, we'll run 0 to 7. We've exhausted our 8 digits, so then we have to roll over. Now we go to 1, 0. So a word of caution, don't call that 10, call it 1, 0. When we look at a decimal number, we learned a long time ago the difference between the digits, which we have a choice between 10, and the weight that each digit contributes to the value. And the weight is determined by the column that that digit appears in. With a decimal number, we're all totally familiar. It's the ones column, the tens column, the hundreds, etc. In a mathematical perspective, you may consider it the 10 to the 0 column, the 10 to the 1 column, the 10 to the 2 column. So the base is what's setting the weight for each of the columns. When we move to the right of the decimal point, now we're dealing with fractions. So the first column is 10 to the minus 1, the second column is 10 to the minus 2, etc. So when we look at those, we can sum up all the contributions and we get the value. So if you want to look at a binary number in the same light, we keep in mind that now we only have 2 digits with which to represent our values, zeros and ones. The same principle holds that it's the column that each digit appears in that determines the weight or what it contributes to the value. The columns are numbered identical to the decimal numbering, but the difference is now it's a base 2. So the first column is 2 to the 0, 2 to the 1, 2 to the 2 as we move to the left. So you can think of it simply as the 1's column, the 2's column, the 4's column, the 8's column. And when we move to the right of the binary point, now it's 2 to the minus 1, which we know is a 1/2. 2 to the minus 2 is 1/4, 2 to the minus 3 is 1/8, etc. So we want to look at a binary value. We could then use this type of computation to determine the decimal equivalent, sum them up, and what we have at the bottom is the decimal equivalent of the binary value shown above. Please keep in mind any use of fractions will be very minimal. I do want you to be able to demonstrate you understand what's happening, but there's not going to be any major computation with them. Octal numbers are the same as binary numbers. The difference is the columns are now represented by powers of the number 8. So we have 8 to the 0, 8 to the 1, 8 to the 2, and going to the right it's 8 to the minus 1, 8 to the minus 2. So primarily we're not going to be dealing ever with fractions for octal or hexadecimal numbers. But now in the hexadecimal world, the base is 16. So the first column is 16 to the 0, the next is 16 to the 1, 16 to the 2. And so you see how much each digit in that particular column contributes to the overall value. We'll spend more time on this. The first page here is just introducing some simple arithmetic operations using binary values. And here we're just dealing with scalars. So coming across the top row, we have 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. And 1 plus 1, of course, we know that's 2, but in a binary world, it would be a 0 carry 1. So 1 plus 1 is 0, carry the 1 to the 2's column. When we look at subtraction, it's similar. 0 minus 0 is fine. 1 minus 0, no problem. Where we get into a little trouble is in the third representation where we're trying to subtract a minus 1 from a 0. Of course, we have no 1s to give, so we have to go to our neighbor to the left and borrow. And when we borrow, we would borrow a 2 because we're taking it from the 2's column. When we bring that 2 back to the 1's column, we can then subtract 2 minus 1 to get our 1, but we need to then indicate that a borrow has occurred. On the last digit is 1 minus 1 is 0. Dealing with vectors, it's similar, just requires a little bit of ability to be able to move through the values. So starting with the addition on the top, 1 plus 0 is 1. 1 plus 1 is 1, 0. So we drop the 0, carry the 1. Now we have 1 plus 1, again, drop the 0, carry the 1. 1 plus 1, drop the 0, carry the 1. So just a little bit of concentration, you can be able to do that easily. With subtraction now, 1 minus 0 is 1. 1 minus 1 is 0. We try and subtract 0 minus 1. We cannot do it, so we're in the 4's column. So we have to go to the 8's column where we bring an 8 or 2 4's back to the 4's column. So we have 2 4's minus 1 4 gives us 1 4. And now we have no more 8's left over. So that is the answer there. And multiplication will be shown a little bit better on the next slide. So here are some values you can exercise and make sure you understand it. With multiplication, it's always here. The first digit's a 0. I drop the 0, drop the 0. Now I drop the 0 and just begin to pop. I take this 1, multiply it by this value, and stick it here. And as I successfully do it, I bring my zeros over, sum it up to get the product. Some simple digits when dealing with binary numbers can be seen from this simple example where we look at an absurd amount of money to mow someone's lawn. So if I said I'll give you $4,001 to mow my lawn, of course you're very interested, but what are you interested in? You're interested in the 4, because that represents how many thousands. The 1, you're not so interested in it. So we would refer to the 4 as the most significant digit. We would refer to the 1 as the least significant digit. With binary numbers, now we refer to it similarly but a little different. On the left, we have the most significant bit, and on the right, we have the least significant bit. Oftentimes, we just refer to the most significant bit as the MSB and the least significant bit as the LSB. When we're converting between binary, hex, and octal, the key is to keep in mind 4 binary digits makes 1 hexadecimal digit, 3 binary digits make 1 octal digit. With that understanding, you can move between any combination of binary, hex, and octal. If you start with hex, the recommended approach is to go to binary, then to octal. If you start with octal, again, the recommended approach is to go to binary, then to hexadecimal. The trickiest part is when you're dealing with decimal numbers. So I provide in this presentation 2 ways to do it. The way I like, that's simple and straightforward, is I take the value I'm converting, I find the largest power of 2 that fits, I designate that it fit with a 1, then I walk down every power of 2 till I'm done and keep track of the ones that fit. So I had 256, so that means I can take 256 out. I have 227 left over. I have 128, so I put the 1. I can now subtract that, and I get 99. And as I continue down, let's say after I found a 32, my leftover is 3. I have no 16s, so I put a 0. I have no 8s, I put a 0. I have no 4, I put a 0. But of course I have a 2 and a 1. And when I write the number, the first one I wrote is the MSB. The last number I wrote is the LSB. A second approach that students seem to like is to take the number that you're going to convert, the decimal number, and just begin dividing by 2. Where there is a remainder of 1, you write 1. Where there is a remainder of 0, you write 0. And as you work your way down doing the division, the number will be created in the right-hand column. The difference is now the first digit you generated is the LSB, and the last digit you generate is the MSB. So when you write it down, you start at the bottom and go up to the top. So we've considered decimal, binary, octal, hexadecimal. You should do your best to memorize the binary equivalent of the first 16 hex digits. At least be able to regenerate them quickly. And when you want to convert from octal to hex to binary, always start at the LSB of the binary number, group by 3s to get an octal digit, group by 4s to get a hexadecimal digit. We talked a little bit about codes. Here's the representation of a binary coded decimal. It's somewhat of a dated concept, but it allowed the designers to have a device that would take a value and give a binary code that could then be displayed. So it only dealt with, since as it's called, the binary coded decimal. There's only 10 decimal digits, so there's only 10 codes that went along with it. More common is the ASCII code, a 7-bit ASCII code. The table shows 4 columns. Each column has a decimal number, a hex number, an octal, later the HTML, then a character and a description of the control characters. So what this means is that these were values that would be sent to a modem or to a terminal and would be interpreted as something to be displayed, not something to be computed. The example would be if you sent a hex 41, the receiver would say, oh, that's capital A, and it would display or send a capital A. Another code is what's called parity bits, and I'm going to go through this very simply. Serial communication means that you're transmitting from a sender to a receiver 1 bit at a time. The concern is that how does the receiver know that it has received the data that the sender sent? One way was that the sender would include a bit called the parity bit that would be used for error checking. So the scheme was you would count the number of ones, and if the number of ones, including the parity bit, was even, you would say you had even parity. If the number of ones, including the odd, was including the parity bit was odd, you would say you had odd parity. So the transmitter would send the data along with the parity bit. The receiver would collect all the bits, regenerate the parity on the data bits, then compare his result to the parity bit that was sent to determine whether or not he got it right. Parity is pretty weak, but they used it quite a bit. So that is a simple overview. Hopefully that will help you in your studies.